Thank you, Dr. Yuri, for this invitation, and thanks also to the IET UK for this invitation to give this talk on fuzzy modeling and the problem of reverse estimation of class of nonlinear systems. So I am a professor at the University of Paris-Saclay. My research focus mainly on control theory, fuzzy modeling, LPV approach with some extension and some results and some development theory on fault detection and isolation, fault tolerance control, applied to nonlinear system in general, and also by considering multi-agent systems with some application in transport on vehicle domain particularly. So my presentation of today will be focused mainly on fuzzy approach, particularly on the so-called Takagi-Sokino approach, TS approach. So this talk starts by firstly by defining the context and the motivation of this talk. Indeed, the relation between AI, artificial intelligence, fuzzy logic, and soft computing will be briefly introduced. Then the fuzzy modeling, particularly a class of nonlinear system, the so-called TS approach, and how to design observer, particularly in known input observer, because it is applied extensively in fault detection and isolation and fault tolerance control algorithms, and to develop some strategy in fault tolerance control strategy by focusing on how to design these observers in with LMI formulation. So LMI formulation will be discussed in this presentation. So firstly, some classical results exist and will be presented in this talk. Mainly the result in full frequency domain, which means infinite domain. Then the limitation of these classical results will be discussed to introduce the aim of this talk, namely the finite frequency domain approach, their objectives, and its motivation. So my presentation will be focused mainly on fuzzy approach, particularly on TS approach in finite frequency domain at the end of the presentation. So next, how to design in known input observer in finite frequency domain will be presented. The multi-objective synthesis in terms of sensitivity to faults and robustness to disturbance will be discussed also. And I'll finish with illustrative example and some perspective. The first work on fuzzy logic was published in 1973 by Lotfi Zadeh, where the idea is to approximate the behavior of complex systems by some rules when the model is not available. Later, the soft computing, which include the fuzzy logic, neural network algorithms, or meta-heuristic algorithms, as well as their combination, is introduced. And for example, the paper, the paper of Dubois and Brad gives a good introduction about this domain, where the soft computing is presented as a part of an artificial intelligence. And the combination of these two techniques can provide an intelligent system with more ability and flexibility. In the other work, this one, a short overview of artificial intelligence and its relation with fuzzy logic is provided. Okay. So for those who do not know or not familiar with this approach, it is a question of well-known polytopic approach, which can be obtained by the decomposition of the operating domain of the nonlinear system into linear subdomain, linear zones, and then the global nonlinear behavior is obtained by convex optimization of this linear system corresponding to linear areas. So why this decomposition? Simply, the goal is to use numerical tools of the convex optimization, such as LMI toolbox. This is the main objective, and then formulate the design problem, controller design, observer design, or any strategy in using convex optimization and linear matrix inequality tools. This representation can, as I said before, can obtain it by decomposition into linear system, and by interpolation we approximate the nonlinear behavior of the system, but can also obtain by direct mathematical transformation from a nonlinear model to an interpolation of this linear model. This representation can also obtain it directly from input-output data without any mathematical nonlinear model. These methods of transformation are similar for continuous time or discrete time modeling. So it is the same methods. My presentation will be focused on the TS approach. This approach, as I said, it's obtained by convex interpolation of linear system, as you can see here, by interpolating the different linear zone, and each zone is represented by a linear model, LTI model, and where the activation mu, the interpolation function or the activation function, obey to the property of convexity, which means that the sum of these functions, mu, it's a scalar function, their sum is equal to 1. Okay, this is the constraint. So to obtain this model is generally very easy when we have a nonlinear model, and you can find it in many references, as I'll show in this presentation. This approach has been extended in recent decades to the polynomial TS model, where each local model, in this case, is not linear, but it can be polynomial, as you can see here. So it is an extension of classical TS model. Or then we can talk about polynomial TS model. Okay. And in this case, we use the SOS toolbox under MATLAB. You can find it. It is the toolbox under MATLAB. This toolbox is used to solve the control problem as similar to LMI toolbox under MATLAB. And this approach, the SOS approach for a polynomial TS model, lead to less conservative. This approach leads to less conservative results in terms of design problem. This class of nonlinear system is not considered in this talk. I consider only the classical one, where the linear model is where the local model or the zone is in linear form. Okay, this reference is the first one where we consider that the TS TS model, where the local model is in state space representation, like this representation. This approach is quite interesting, since it can include the LPV approach, the TS approach, which will be considered in this talk, or the switching approach, where when the interpolation function, the interpolation in this one, take 1 or 0. As I said before, the goal of this approach is to use numerical tools of the convex optimization, such as LMI toolbox under MATLAB. So many control problems are formulated, and the objective is to formulate all the many control problems in LMI design condition or SOS design condition when we consider polynomial TS model. And generally, it is easy to solve this design condition when we can obtain LMI condition. The aim of researcher in this domain is to reduce the conservatism of the obtained algorithms, since all these developed results are sufficient only, so we can improve the results. Some basic concepts of this approach can be found in this personal book, particularly for young researchers or engineers interested by this approach. Indeed, with the framework of this approach, the goal, in general, the goal is to develop algorithms, obviously to estimate or to control the system, but also to develop some algorithm for fault detection and isolation, and also for a fault-tolerant control strategy, to develop some strategy for some fault-tolerant control strategy, in order to maintain or allowing systems to continue operating properly in presence of faults, and then avoid dangerous situation for nonlinear systems subject to actuator fault or sensor fault or component fault in general. For example, avoiding vehicle rollover. Rollover situation is classical one in the vehicle domain. For example, in our laboratory, this approach has been extensively used. The TS approach has extensively used in vehicle domain for driver assistance, the control of vehicle dynamics, in collaboration with local industry and university in France and abroad. Now, to give an example, to give you an example of design problem using this approach, I consider the following problem. I consider the problem of how we can design an observer for TS systems subject to unknown input. For example, U bar here can be, it is the unknown input. It can be, in practical situation, can be fault, actuator fault, or sensor fault, or any external unknown input. And we consider that the development part, the first step is solved by transforming the nonlinear system into TS system. And for this system, we consider the following structure of unknown input observer, okay, where there's gain in red colors. In red colors must be the design. As you know, the unknown input observer have been widely studied in, and many works have been published in linear case with different approaches. The objective here is to obtain linear conditions that are easily implemented for nonlinear system. This is the objective. And the objective here is to develop unknown input observer for nonlinear system, not for a linear system. So in the case of TS system, with the presence of the unknown input, the considered structure of the observer is like this one. So we can see here the function mu is the same. Okay, you consider the same function similar to the TS system, the same. So the only the gain N, G, L, and E must be designed. So the goal, excuse me, the goal is to calculate this gain to ensure asymptotic convergence despite the presence of unknown inputs. Okay, this is our objective. So indeed, by considering quadratic Lyapunov function and its derivative, design condition in LMI form is obtained like that, like this. The proof is not considered here, but you can find it in, for example, in the book I presented before, or in references that I can give you at the end of the presentation. So the proof is very easy. You can consider the error of the error of estimation, the dynamic of the error of estimation, and the quadratic Lyapunov function. And by deriving the time derivative, by considering the time derivative of the Lyapunov function, we obtain this formulation, which is in linear form, because this inequality is in linear form. It is an LMI form in LMI conditions with those constraints in inequality form, but it is in linear form. So there's linear condition contain equality constraints, okay, where the matrix equality allow to make the estimate independent of the unknown input, and the other part, the LMI condition, ensure that the asymptotic convergence of the estimation is guaranteed. Okay, so we have two parts in this in this formulation. The first one, LMI, is to ensure the asymptotic convergence, and the two last equalities is to run the estimation independent of the unknown input. Okay, so with this condition, we can solve this problem easily, and we can obtain the gains of the observer, like here. We see here in this equation. We must know that with this condition, it is easy to introduce performance criteria by pole placement using LMI region. The performance criteria are not presented here, but can be found in many published references or in the book I cited before. Some extensions are also studied in the literature, like the challenging problem of unmeasurable variables. As I presented before, for the observer, I consider the results I presented before, consider that the activation function or the interpolation function mu are known, but in some situation and in practical case, this function can depend on non-enumerable variables. So this case called unmeasurable variables is a challenging one, but we can find some interesting results considering this situation. We can also consider the case of polynomial TS system by extending the last result to this class of nonlinear system, and we can solve. We can obtain some SOS condition that can be solved easily also by using SOS tools under MATLAB. And also we can consider challenging case by including disturbances and fault estimation and estimation of the unknown input U bar, for example. Some results consider also the estimation of the unknown input U bar. Okay, so this formulation contain the case of actuator fault or sensor fault subject to external disturbances, and we can find some results to solve this problem. These issues are not addressed in this presentation, but I can provide some references if necessary. These unknown input observer have been applied successfully in a variety of applications, particularly in the vehicle domain, by estimating vehicle dynamics variables and other attributes such as road curvature, or road bank angles, and by estimation of road bank angles by using the unknown input observer. For example, this simulation represents the estimation of side slip angle and yaw rate angle, and you can find the result in this paper in Vehicle System Dynamics journal in 2015. If you are interested by more details about this study. It is experimental study implemented on Renault vehicle with the company, with the local company collaborating with our university. This observer have also found applications in the field of cryptography and the synchronization of chaos, like this international collaboration. So it is just to say that the unknown input observer can be applied in different situations for synchronization of chaos in vehicle domain, for estimation of unknown input, and also applied for developing some strategy for fault detection and isolation and fault tolerance control. This slide presents an example of how to generate fault tolerance algorithms in the presence of uncertainties, for example, where the nonlinear system is uncertain, in presence of delays, saturation, and also disturbances. This case represents only the case when we have actuator faults. Okay, you know, in the field of fault tolerance control, we know that there are many strategies. The most classical one is that based on a bank of observers in order to locate faults. The less obvious methods are those based on estimation of fault. There are more because there are more complicated from a methodological point of view, but it is also based. Some results are based on the design of unknown input observer, allowing to estimate simultaneously the state of the system and the unknown input. Another FTC approach, this one that we can see in this slide, is based on a reference model that also incorporate fault estimation. As you can see here, the observer can use also to estimate faults if you want. You can find more detail in this reference. This approach is very interesting because it can be used in trajectory tracking, which can be used in applications such as autonomous vehicle, for example, following some trajectory. As I said before, all these results are sufficient only and can be improved by reducing some conservatism introduced by the LMI formulation objective. This is the example of the control law that we need to develop by calculating the gain K and taking into account the uncertainties, for example, the saturation of the actuators, or taking into account the delay. This is another example of fault-tolerant control strategy applied to VTOL systems. Just to show that there are different strategy, and if you are interested by more detail, you can, for example, you can see this reference in Journal of European Institute, where we have the development of the nonlinear model to TS model, and the design condition in LMI formulation with how to obtain the gains of the controller and the observer, and the implementation with some simulations. So as you can notice, all these works on state and fault estimation omit any information on the frequency domain in which external disturbances and faults evolve. All this presented method and the one I presented before are intended for infinite frequency domains, which in some cases lead to some conservative results. It is why the idea is how to introduce the information about the frequency domain of fault and disturbance in the design condition. So in order to avoid the conservatism of these results, the idea is to introduce the frequency domain of faults and disturbances, and it is the objective of this discussion. So, for example, you can see here you have fault and disturbance in 4 frequency domain, and now, as you can see before, the LMI design condition is dependent only on the parameter or the parameter of the system A, B, C, and the objective is to calculate the gain N independently of the frequency domain of F and D. Okay. In order to go further and reduce the conservatism of some existing results, the idea is to incorporate the frequency range of the external signal F and D. Okay. The idea is to incorporate this frequency into the synthesis conditions of observer or controller as well. In this talk, I present only the problem of how to design observer, not controller. But the result can be extended to design controller in finite frequency domain also. So this work was initiated by my former PhD student, Dr. Shibani, and published in some international journal like these references. Okay. As has been said, it has been shown in several research works that the finite frequency method generally leads to more efficient results and less conservative condition. And the basic idea of this approach is inspired by this work of Iwasaki and all. This work who established the equivalence between the frequency domain inequalities, like transfer function, which depended on the frequency, and and the equivalence between frequency domain inequalities and linear matrix inequality for linear system. It consists of considering, and this approach is consisting in considering three domains or areas of frequency: low frequency ranges, middle frequency ranges, and high frequency ranges, which allow to consider the full frequency domain from low to high frequency domain. And so the idea is based on this decomposition of three domains. So generally, when we consider frequency and disturbances with different frequency domain in from theoretical point of view, we need to consider nine domain by combining the three domain for fault and disturbances. But in practice, generally, the fault and disturbance belong to one domain, and we can use only one theoretical result, not the 9 results. But from theoretical point of view, we can consider the nine possibilities. Okay. One might question the motivation behind this approach. In other words, how is this approach useful beyond the theoretical aspects and beyond the reduction of conservatism? Because, as I said before, the idea to use the finite frequency domain is to reduce the conservatism, to have more chance to design a controller and observer. It is the first objective, to reduce the conservatism. But the question is, what is the motivation behind this approach? To answer this question, one of the motivation is, for example, the problem of comfort in the field of the vehicle. Indeed, since we know, since the sensitive range of the human body is located in a very specific frequency band, generally between 4 and 8 Hertz, the synthesis of observer or the controller can be limited to this frequency range. It is why, in some cases, this approach, finite frequency domain, is more interesting to consider. Obviously, we consider this approach when we can't solve, when we can't find a solution in a full frequency domain. But if you find a finite result, we can design we can solve the problem of design in full frequency domain. It is not necessary to consider a finite frequency domain. We consider this approach when we can't find a solution. So the objective thereafter is therefore how to incorporate, it is the main objective, how to incorporate the frequency range of external signals into the synthesis conditions for synthesis condition mainly for observer design and controller design. But also when we consider multi-objective problem. For example, when we are looking for an observer sensitive to faults and robust to the disturbances. In this case, it is multi-objective fault detection and isolation, because in this case, the observer must estimate the state variables and, if possible, the faults, but also to design a residual generator called also health indicators to be sensitive to faults and robust to disturbances. In principle, as I said before, from a theoretical point of view, it is necessary to consider the three ranges of frequencies: low, medium, and high frequencies for faults and disturbances, which make 9 combination. Okay. In practice, in theoretical point of view, for using this approach, and generally we can find some papers, some references considering only one situation, but you can find also some paper considered online combinations. So it depending on the paper and the problem that we want to solve. Based on all the above, of the above, we can summarize the objective as follows. For a TS model, like the one, but the matrix is the sum. It is just to simplify the equations. Here we have a row is the sum of mu ai, the sum of mu function, the interpolation function bi, and so on. Okay, and for this TS system subject to sensor fault, actuator fault, and disturbances, we need to design an observer with the same structure as before. It is the same structure for as we studied before for full frequency domain, and the objective is to design this observer in order to estimate the state of the system, okay, by guaranteeing that the asymptotic convergence of the error of estimation, and also by generating a residual signal sensitive to fault, by minimizing the parameter gamma, okay, and also robust as possible to disturbances the sensitivity is by maximizing beta and the robustness against the disturbance by minimizing the parameter gamma. Okay, the idea is to reject the disturbances from the residual signals, but to render this residual signal sensitive as possible to fault by minimizing the parameter beta. It is why this problem is called multi-objective problem, because the idea is not only to estimate the state and in some situation estimate also fault, but also to develop some the residual signal sensitive to fault by maximizing beta and robust against the disturbance by minimizing the parameter gamma. So it is multi-objective problem. So these objectives can be summarized as follows. It is the same problem. It is the same problem, but it is just summarized differently. So for filtering error, the error of estimation, filtering error is the error of estimation. For filtering error free to disturbances and faults, the asymptotic convergence should be guaranteed. Okay, and for filtering error dependent on disturbances only, disturbance should be rejected as possible by minimizing the parameter gamma. Okay, and for filtering error depending only on faults, the residual signal should be sensitive as possible to fault by maximizing the parameter beta. As you can see here, I consider only the middle frequency domain and low frequency domain, but the definition is for all domain. But just here to show that I'll consider for in the following only this situation, because I can't consider the 9 possibilities. So I consider only this situation where the disturbances is in the middle frequency domain and where the fault is in low frequency domain. But we can consider the different situation, one from the different 9 possibility. In principle, it is, as I said before, it is necessary to consider the 3 ranges of frequencies: low, medium, and high frequency for fault and disturbances. Okay, but to simplify the presentation, I will not present all these cases or 9 cases because I consider fault and disturbance. We have 3 cases if I consider only fault and or only disturbance. But if I consider disturbances and faults, we can have 9 combination possible from theoretical point of view. So to simplify this presentation, I will not present all those 3 cases, but rather a case that often arises in practice. That is to say, the case of medium frequency disturbance and low frequency fault. Okay, so you can find, if you are interested by this result, you can find it in this presentation, where in this work, where we consider TS fuzzy model in finite frequency. We consider also the case of polynomial TS model also. Indeed, to illustrate this approach, the following TS model, just I think to finish my presentation with this case, the following TS model with 2, as you can see here, with 2 local models subject to faults and disturbances is considered, where only the case of a medium frequency disturbance between omega d1 and omega d2, and a low frequency fault defined by omega f1. Okay, so I consider only this case to illustrate this approach. Okay, so we are in the same situation. We have a nonlinear system represented by a TS model subject to unknown to fault detection, to fault actuator and fault actuator and fault sensors, and with external disturbances. And the idea is to design an observer or a fault detection filter. It's the same. In our situation we consider the unknown input observer approach, and the idea is to consider a multi-objective problem by considering the estimation of state of the system, the faults if possible, and designing also a residual signal sensitive to faults and robust against the disturbances. It is the objective. So for this TS model with 2 local models subject to fault and disturbances D, we consider the following data of the following matrices of the system. It is just an example of to illustrate the approach. We can see that also the fault, the considered fault in this situation is has this shape. We can verify that there is no solution to design an unknown input for this system using basic results. The first results in LMI formation that I considered in the beginning of the presentation, where the frequency domain is not considered. I mean that the design condition which do not include the frequency range of the unknown inputs cannot provide a solution for this example. Okay. For this example, I can't find the solution by using the classical one. However, by considering the developed result for the frequency domain, we can find a solution as we can see here. So by considering a disturbance signal and the fault signal with the following frequency ranges, this disturbance belong to middle frequency and faults belong to the low frequency domain. And by solving the design condition in finite frequency domain, we get the following solution. And the unknown input is completely defined by minimizing gamma and maximizing beta. So the design condition is not presented here, but we can find it in the reference that I presented before. It just to simplify the presentation for you, but you can find it in the reference that I presented before. This one, you can find the design conditions in these references, or in this one in Automatica, or in the TFS reference. It's the same. And as you can see here, we obtained some simulation by considering the finite frequency domain design condition. And to show this fact, the following simulation show that we can improve considerably I don't know why. Yes, I look for this simulation. The following simulation show that we can improve considerably the algorithm performance and the fault diagnosis. We can notice that H minus performance increase the sensitivity of a residual signal to the fault of the residual signal. Okay, you can see here that we have two simulations without the H minus performance. It means without maximizing the parameter beta, and here by maximizing the parameter beta. And you can see that we maximize the sensitivity of the residual signal to fault. So it means that we can detect easily the fault, and then we can develop some fault tolerance control strategy. And you can improve the quality of and the performance of the designed observer and design controller. In addition, as shown above, for many applications, as I said before, there is no solution if the finite frequency domain approach is not considered for this exam. So for some situation, this approach is very interesting to find some solution, and particularly when we consider the multi-objective synthesis. I mean the problem of estimation, the problem of estimation of state, and the problem of estimation of faults, and by designing some residual signal sensitive to faults and robust against the disturbances. Future research focuses on more complicated nonlinear systems, such as multi-agent systems or cyber-physical systems. The goal is to extend some of these results for distributed fault detection and isolation, and fault tolerance control problem for example, multi-agent system. Some other results also consider fractional order system, and particularly for singular fractional order system. And in order to take into account the complexities related to cyber-physical system or multi-agent system, such as data transmission, sampling, etc., we have developed in recent years some collaboration on event-triggered control and event-triggered estimation in collaboration with different university. And recently we have some PhD thesis defended recently in this domain, like the thesis of Zhuan Wang defended in last November 2025. For more detail, here are some personal references related to this talk and the perspective works. So thank you for your attention. Thank you very much for your invitation. Your questions and comments are welcome. I am also open to discuss future collaboration or answer your question by emails. So you can contact me by email if you want. My email is this one. Thank you very much for your attention.